In this lecture, we are going to continue looking at the previous notebook, in which we look at the ACFs and the PACFs of signals we generated ourselves to test that our methods of choosing ARIMA orders actually works. So since we've already looked at the PACF, this lecture will focus on the ACF and moving average models. We'll start by plotting the ACF for IID noise. Note that we are now using the function plot ACF instead of plot PACF. However, the syntax is the same. Alright, so what do we see? As expected, there is no autocorrelation between any point in the time series and any other point. Therefore, the autocorrelation is 1 at lag 0 and 0 elsewhere. Next, we're going to generate an MA1 process. We'll start by creating an array of size 1000 with samples from the normal with mean 0 and standard deviation 0.1. We'll call this array errors. As you recall, the MA1 process is generated by adding the current error plus some coefficient times the previous errors. So next we'll create an empty list called MA1. Then we'll enter a loop that goes for 1000 iterations, the same size as our errors array. Inside the loop, we'll check whether the loop iteration index is greater than or equal to 1 or not. If it's not, then it's 0, which is a special case. For I greater than or equal to 1, we just have the normal MA1 equation. Again, I've chosen the coefficient 0.5 arbitrarily. So the current value in the time series is 0.5 times the previous error plus the current error at index I. If I is equal to 0, we have the else block. Note that when I is equal to 0, there is no past value, therefore it's not possible to add any previous error. Therefore, for the first iteration, x is just equal to the first error. Outside the if statement, we append x to the list MA1, and then outside the loop, we convert our MA1 list into a NumPy array. In the next block, we plot our MA1 process. Note that again, this kind of just looks like regular noise. It's generally very hard to tell whether something is an MA process or an AR process just by looking at a stationary time series. The next step is to plot the ACF for our MA1 array. Alright, so as you can see, we have one non-zero ACF value at lag 1, which is what we expect. If we were to do this in reverse order, that is, use the ACF plot to find the order of the MAQ process, we would look at this plot and choose Q equals 1, because that's the maximum non-zero value. Next, we're going to generate an MA2 process. Again, this code is very similar to the previous code, except that now, the current value in the time series depends on 3 errors: the current error, the error at lag 1, and the error at lag 2. I've given the error at lag 1 a coefficient of 0.5, and the error at lag 2 a coefficient of minus 0.3, same as the AR2 process from earlier. Note that this time, I didn't bother to account for the early values in the time series as special cases. Recall that in NumPy, if you index an array with negative values, it just loops back around the end. Since those values are random anyway, it doesn't really affect our results in any negative way. Therefore, I've decided to keep the code like this for the sake of simplicity. So there are no special cases for I equals 0 and I equals 1. Next, we plot our MA2 process as a time series. Again, it just looks like regular noise. Next, we plot the ACF. Alright, so we see what we expect. There are non-zero values at lag 1 and lag 2, which would mean that we would choose Q equals 2. And we know that this is true because we just created an MA2 process. Next, we're going to generate an MA3 process. The weight for lag 1 is 0.5, the weight for lag 2 is minus 0.3, and the weight for lag 3 is 0.7. Other than that, this code is the same as before. If we look at our time series plot, I would say that there is still no discernible difference between this and the other plots. Next, if we look at the ACF plot, we see that the largest non-zero lag is 3. Note that there is one other non-zero lag at 25, but again, as per what we know about statistical testing, this is supposed to happen about 5% of the time. If we saw this plot and did not know that we were dealing with an MA3 process, we would still probably choose MA3 rather than MA25. We know intuitively that MA25 is probably unlikely, and we would also prefer a simpler model. We also see that this value is not that far outside of the confidence bounds, so most likely we would just ignore this as a fluke. Next, we're going to generate an MA6 process. Alright, so this time, I'm not going to read you the weights, but you can feel free to make note of these if you would like. When we plot the MA6 process, we see that it still pretty much just looks like all of the other stationary time series we've looked at. Next, we plot the ACF for our MA6 process. As you can see, the largest non-zero lag is at lag 6. Notice how at lag 4, the value does not go outside the confidence interval. However, we would most likely not consider this an MA3 because of the significant non-zero values at lag 5 and lag 6.